Okay, one other thing, just in case you want to work this from a different angle. Let's assume you have something like this. We have a irrigation system, and that irrigation system spins around a pin. All right, now that irrigation system, let's assume it takes 27 minutes to go all the way around. So 27 minutes to go all the way around, and let's assume this is 25 feet, and out to here would be 50 feet. And out to here would be a full 75 feet. All right, now what we want to do is we want to find linear velocity, angular velocity, and RPM. Now, in this particular case, the easiest thing to start with is not linear velocity because I don't have a distance. I do have a time. I don't want to do angular velocity because I don't have like, oh, it goes 120 degrees or it goes 3 pi over 4, whatever it happens to be. What I have is I have a time that it takes to go one revolution. So if it takes 27 minutes to go one revolution, then I need to figure out how many revolutions in 1 minute. All right, so to figure out one revolution in a minute, all I got to do is set up one revolution in 27 minutes. Because if I need RPM, I need the revolutions on top and I need the minutes on the bottom. So in this particular case, I have one revolution in 27 minutes. So I really don't have to work very hard at this. All I have to do is a simple division. And so I simply say, in this case, 1 divided by 27. And so I have 0.037 revolutions in a minute. So that equals 0.037 revolutions in 1 minute. All right, so that is our RPM. Now, 0.037 RPM. Okay, now we need omega. Now, to get to omega, omega is going to be measured in radians per minute. Well, how do I get from revolutions to radians? Well, that's actually fairly simple because all I have to do is take 0.037 revs over 1 minute. I need to get rid of revolutions, so I'm going to put 1 revolution on the bottom. And how many radians are in 1 revolution? The answer to that, of course, is 2 pi. So I simply multiply that by 6.28. Answer is 0.23. Yeah, what's called 0.23. So I have 0.23 radians per minute. Now, that's all well and good because whether it's the sprinkler here, here, or here, they are moving all at the same speed in terms of rotational energy, RPM, and radians per minute. What's changing is how many actual feet it takes to get to a certain spot. So obviously, the farther out from the center, the more feet it takes. So I don't need 1 linear velocity. I actually need 3 linear velocities. So in this case, I'm simply going to say V equals omega R. And so V is going to equal 0.23 times 25. For here, V equals omega R. So that's 1, that's 2. So V2 equals 0.23 radians per minute times the radius of 50 feet. And finally, V3 is simply going to be 0.23 radians per minute times 75 feet. Now, this is important because you're going to end up with feet on top, minutes on the bottom. And so from there, I simply plug those in, and those are my 3 numbers right there. And I'll let you take care of that, plug it in. So whether I'm going from a distance in a given time or if I'm going 1 revolution in a particular number of minutes, it's not that challenging to move back and forth between the 3. And I've really only used the 1 formula. Everything else has just been unit analysis. So with that, take a look, see what you can do with that.